Okay, so what we're going to talk about today is something called normal distribution. Really, normal distribution is the symmetric distribution that we were speaking of the other day. Okay, so when you look at a distribution of scores and they are approximately symmetric, where it looks like they're kind of equally balanced on either side of the mean, that's what we refer to as a normal distribution. And when you're told that it's normally distributed, you can actually rely a little more on like certain percentages that fall in that diagram to be able to know, is this a normal value, an abnormal value, what percent fall above or below. So remember, we also talked about standard deviation. That was a way of, determining the spread of a data set. So if you take a look at the diagram that I have right here, this normal distribution, the 0 in the middle is the mean, okay? Standard deviations are these 0.5 and 1 and 1.5, and that's talking about how far away a data value is away from the mean in terms of standard deviations or z-scores. That's basically what those z-scores are. They're standard deviations. So if you remember the other day when we were approximating standard deviation, we got that from doing range divided by 6. Well, if you look at 3 standard deviations to the left of the mean, that's what -3 would be. 3 standard deviations to the right of the mean, that's what 3 would be. That's a total of 6 standard deviations in total in a diagram like this. So if I take what should be, and everything like within these 6 standard deviations should be the majority of your data, like 99.9% or 0.8%, something like that, of your data falls within these 6 standard deviations. So 3 to the left and 3 to the right. So that's why that should be about the range of your data set divided by 6, and that was a way of approximating each individual standard deviation. So again, we're going to now refer to these standard deviations as z-scores. So how can we actually use those to find, probabilities or percentages? So if you look down below, example 1, for a population that is normally distributed, you need to see that keyword in order to be able to use that diagram. And by the way, I'm initially going to use the diagram itself, and then eventually I'm going to shift the stuff in the calculator to be able to assist you with doing these calculations, especially when things don't fall at nice z-scores like 1 or 1.5. So for a population that is normally distributed, find the percentage of the population that lies within 1 standard deviation of the mean. That means in your diagram, everything that's within 1 standard deviation to the left of the mean up to 1 standard deviation to the right of the mean. That's what it means to be within 1 standard deviation, and you add up all the percentages that fall between those 2 points. So in this case, you're going to be adding up the 15, the 19, whatever, the 15, add all those together, and when you add those up, they come out to be approximately 68, well, really 68.2, but about 68% of your data. So you can see right there, that's more than half your data falls within 1 standard deviation of the mean, and that's what should happen. The majority of your data should be clumped close to the mean, and again, remember the mean is considered to be 0. Within 2 standard deviations of the mean, so between -2 and +2 this time in terms of standard deviations. So if you add up all of these percentages and add them all together, that comes out to be roughly 95% of your data. So now 95%, we had referenced that the other day when we were doing that problem with the compy heights and a normal window and abnormal window. Well, this -2 to 2 window is special because that's the normal interval. That's considered a 95% confidence interval. Things that fall outside of this -2 to 2 window are considered to be abnormal. Okay, and again, we're going to get more into drawing conclusions in our next couple lessons, but I want you to keep in mind, anything within that -2 to 2 window is considered to be normal. Anything outside of that is abnormal. And again, we'll do more with that when we get to drawing conclusions. Let me just skip to one more example, and then I'll get into ones where we actually use this for context. Between 1 and 2 standard deviations above the mean. So when I look at my diagram, that's specifically between 1 and 2. Okay, it's not saying within this time, it's saying between 1 and 2. So if I add up my percentages between 1 and 2, that comes out to be about 13.6%. So let's get into actually using this to do a problem. At Arlington High School, 424 juniors recently took the SAT exam. On the math portion of the exam, the mean score was 540. Okay, so when you think about your normal distribution, at 0, that's where a data value of 540 would be. So this is going to be sometimes what's a little bit of a challenge, is relating the data values in the problem into z-scores with a standard deviation of 80. Okay, so I'm going to actually make all my values in that normal window between z-scores of 2 and -2. And again, you're technically going up by standard deviation. So to get to 1 standard deviation above the mean, I'm going to do 540 plus 80, which comes out to be 620. And then add 80 again, and you find out a z-score of 2 would actually relate to the value of 700 on the SAT. When I go to the left, 540 minus 80 comes out to be 460. And 460 minus 80 comes out to be 380. Okay, so again, that's how you relate those z-scores to your data values, and I'll talk more about that in a little bit. So it's saying what percent of math scores fell between 500 and 660? Well, you'll notice that 500 isn't a regular z-score value, a whole z-score value. That's actually a z-score of negative 0.5. And between 660, that's also not a whole number z-score values. That's going to be a z-score value of 1.5. So I'm going to add up all the percentage in my picture between negative 0.5, okay, and 1.5. I'm going to add all those together. And when I do that, that comes out to be 62.4%. Now, I want to actually show you how you can start using the calculator for this, especially because you can see right here, you're starting to get z-scores that are not whole numbers. This one, thankfully, we have spaces for negative 0.5 and 1.5, but what if it was 1.2 or negative 2.8 or something like that? So I would refer to this as my lower z-score is that negative 0.5, and my upper z-score of 1.5, and I'm going to show you how you can type this in the calculator and get the same value. So what you're going to do in your calculator is you're going to hit the second button, and you're going to go to where it says distribution. It's right above the word solve. Okay, so let me do that again. Second, distribution. You're going to 2, normal CDF. Okay, so my lower value should be my lower z-score, which is negative 0.5. My upper value should be my higher z-score, which is 1.5. This weird U and O, what that's talking about is the mean. Mean is referred to as mu. It's just like a Greek symbol. And then standard deviations is in terms of 1. So the fact that we're using these values, these z-scores, you just leave that standard deviation as 1. Okay, so you leave those as is, and you hit enter, and you hit enter again. Oh, of course. Second distribution, normal CDF, negative 0.5, 1.501. There you go. And you can see that that comes out to give you a decimal of 0.624, again, which is the same thing as this, as a decimal version of that percent. You'll notice that it gives it to you as decimals because eventually we use this to do certain probabilities, which again has to be between 0 and 1, but you can relate them easily over to the percentage. So let me talk about the next one. If Evan scored a 740 on her math exam, so if you look at the values in the table, 740 is pretty high, okay? It's definitely above that 700, okay? 740 is at 2.5 as a z-score. And we want to know what percent go above 740 or above the z-score of 2.5. So your lower z-score in this case is 2.5. If you look on our diagram, we only go up as high as 3. So for our upper z-score, I just need something that's going to kind of go off the chart to the right. Now, my upper z-score can really be anything that's bigger than 3, but just to play it safe, I usually always pick like kind of a large number. So maybe I'll do 100 this time. But honestly, it would probably be sufficient if you even did like 10. So I'm going to go on my calculator, and I'm going to do second distribution, normal CDF, the second one. My lower z-score this time is 2.5. My upper z-score this time is 100, or again, just something that's bigger than 3. Leave the mean and standard deviation as 0 and 1. Hit enter, and you can see this comes out to be 0.006, right? Which turns into something like 0.6%. And if you go up to our diagram from before, if you add up everything that's above 2.5 on our diagram, that is 0.6%. So again, You can see whether you use the diagram provided or you use this normal CDF thing, you're going to get the same answer. The benefit of using the calculator is that you don't always have things that are nice z-scores. So when it comes to actually finding a z-score, especially if it's not easy to be able to match it up with 1 or 1.5, there's a formula. Now I know the formula is a little hard because it's got all these symbols, so I'm going to rewrite this in a slightly different way. To calculate a z-score, you take the value you're provided, you subtract the mean, and you divide by the standard deviation, okay? That's how you're going to figure out the z-score for a specific value. And then again, you're going to figure out a lower z, an upper z, and you're going to plug that in your calculator to find out what the percentage would be. So if you look at example 3, the prices of printers in a store have a mean of 240. Okay, so there's your mean of 240, standard deviation of 50, and the printer you chose costs 340. So what's the z-score for this printer? The z-score is going to come from value, so the value you have is 340, minus the mean, which is 240, divided by the standard deviation, which is 50. So you can see that that's 100 divided by 50, which comes out to be a z-score of 2. And then hopefully in terms of your diagram, that should make sense. Your mean would have been in the middle, 240. If you go up one standard deviation, you've added 50 to 290, and one more, you add 50, and that gives you to 340. So again, this one thankfully still falls at a nice z-score, but it's not going to always be that case. What percent of printers cost more than the printer you chose? So basically your lower z-score is going to be that 2, and you need to find out an upper z-score that goes off the chart to be your higher value. So like I said, I like to choose a big number like 100, but again, you could pick probably 10 and it would work just fine. So second distribution, normal CDF, your lower z-score is 2, my upper z-score is 100, leave mean and standard deviation is 0 and 1, and that comes out to be 0.022, okay, which is about 2.2%. I'm answering it as a percent because that's what they asked me for. Okay, if it said probability, I'd leave it as 0.022. What percent of printers cost between 140 and 290? So for your lower z-score, you're going to get the z for 140, and for your upper z-score, you're going to get the z for 290. So again, to get a z-score, you take the value you're working with, 140, minus the mean. The mean in this problem was 240. Standard deviation is 50. Okay, so when you do that calculation, that comes out to be -2. For your upper z-score, you use 290 as your value, minus mean, which is still 240, divided by standard deviation, which is still 50, and that comes out to be 1. So again, the fact that these are nice whole numbers, you could still use the diagram we had above and add up all the percentages in this chart. Or you can use the graphing calculator like I'm going to do here, just again to just practice. So second distribution, normal CDF, your lower z-score is -2, your upper z-score is 1, leave mu and standard deviation and mean is 0 and 1, and hit enter, and you can see this comes out to be 0.818, okay, or really 819, or if I turn that into percentage, that's about 81.8%. Okay? So I'm going to scroll ahead to one extra example, and I want to talk again about that normal interval because that's going to be important in the next couple of days that we work on stuff. So example 5, it says the U.S. Department of Agriculture states that the average cost of food for a 14 to 18-year-old male is $261.5 per month. Okay, so there's a mean of 261.5 with a standard deviation of 16.25. It says use your calculator to determine the probability, so these are not going to be percentages this time, you're going to leave it as decimals, of choosing someone whose cost of food is less than 280 or more than 270. So we're going to turn these into z-scores and do those calculations. So less than 280, okay, so we need to find out what's the z-score for 280. You can see that 280 is definitely above the mean, so it's probably going to be something like over here, and that's going to be my upper z in this case because of the fact that we want to find out everything that's less than 280. So we're going to find out everything that's lower here. So for my lower z, I just need to pick something that's like off the chart. So maybe I'll do like negative 100, so it's far to the left. And then we'll calculate the z-score for 280. So if you remember what I had just said, to calculate a z-score, it's value minus mean divided by standard deviation. So the value we're working with is 280. The mean was 261.5 divided by standard deviation, which is 16.25, and that comes out to have a standard deviation of 1.138. Okay, so again, in this case, this is my upper z-score because I want everything that falls below this value. So second distribution, normal CDF. I'm doing negative 100 as my lower z-score. I'm doing 1.138 as my upper z-score. So that's why, again, the benefit of the calculator is that now you'd have to use your calculator to find the percent. Otherwise, you'd just be ballparking values off of our diagram, which is not going to be super easy. Leave that as 0 and 1. And you can see that comes out to be 0.872. Okay, so in terms of percentages, that's like an 87% chance that somebody has a value that's less than 280. But again, we were asked for probability, so we leave it as a decimal. Okay, more than 270. So again, 270 is still somewhere to the right of the mean. So that's going to be where 270 is going to be. And this time we're asking to find out more than 270. So we're going to be going to the right-hand side of this value. So our lower z-score is going to be the one when I have 270. And then our upper z is going to be something that's off the chart to the right. So like I said, I like to use 100. So I'm going to do, my z-score is value minus mean divided by standard deviation. Okay, so when you do that calculation, that comes out to be 0.523. Okay, in my calculator, second distribution, normal CDF. Your lower z-score this time is 0.523. Your upper z-score is 100. Leave mean and standard deviation is 0 and 1. And this comes out to be 0.300. Okay, that's your probability that somebody has a cost that's more than 270, or roughly 30% if you want to think of it in terms of percentages. So you can be doing things that are above a specific z-score, below a specific z-score, or I want to do one last one that's between two z-scores. So between 240 and 275. So you need a lower z-score, which is going to come from doing the z for 240. So value minus mean divided by standard deviation. Okay, your upper z-score is going to be the z-score for 275. So value minus mean divided by standard deviation. Okay, so you can see in this case, your lower z-score is negative 1.323. Your upper z-score is 0.831. And then we go and do our normal CDF thing once again. So again, this is exactly the kind of problem that you need your calculator for, because without your calculator, you would never be able to get these exact percentages. So second distribution, normal CDF, your lower z-score is the negative 1.323. Your upper z-score is 0.831. Leave that as 0 and 1. Enter, enter, and it comes out to be 0.704. That's the probability that somebody's value or cost is between 240 and 275, which is approximately 70% of people. So now again, we're going to get into more of this normal interval type situation. Remember how I said before, anything that's within 2 standard deviations of the mean is considered normal. Okay, that's within the 95% confidence interval. Anything outside of that -2 to 2 range is abnormal. Okay, so somebody is spending $290 per month. I think it's safe to say that that seems like a lot, right? Because it's higher than your mean, a lot higher than your mean. But is it really abnormal? So is it higher than 2 standard deviations above the mean? And that's what we have to figure out. So let's calculate the z-score for this value. Value is 290 minus mean divided by standard deviation. Okay, so let me calculate this. I think I didn't do this one yet. 290 minus 261.5 divided by 16.25, and that comes out to be a z-score of 1.753. So actually, she's not totally justified in her statement. Even though that is a higher value, it's not outside of that normal window, so she's actually not justified in her claim. So no, the z-score is within the normal window, okay, or the normal interval, so she is not justified in her claim. Okay, and I want you to keep that idea in mind. Things that fall within 2 standard deviations of the mean are normal values. You can have normal values that are on the higher side or the lower side. Things that fall outside of this 2 standard deviations are considered abnormal, and that's going to be part of what we get into in the next couple days with drawing conclusions. Okay, thanks for watching.